So hi, I'm Lauren. I'm introducing our next set of speakers. The first one is Bronwyn Woods. She's a data scientist at Duo Security. Her PhD is from Carnegie Mellon in statistics and neural computation. And in addition to security research, she's done work in the NLP and neuroimaging space. A fun fact about her is that she estimates she's biked more miles in her life than she's driven, which you might think is an exaggeration, but she told me an anecdote yesterday, which makes me believe it, about a company meeting they had about 300 miles away, where everyone had to go apply for reimbursement for travel, and she had to go ask what the rate was for biking, because she did that. All right, so here's Bronwyn.
All right, thank you for that introduction. So I'm Bronwyn Woods. Welcome to the post-lunch food coma session. I will try to be engaging enough that we don't all go to sleep. So I'm going to be talking about point process modeling of temporal patterns and user authentication behavior, and my goal is that by the end of this talk, you'll have some idea of what that means. All right, so who am I? I am Bronwyn. I work at Duo Security, as mentioned previously. This you see to the right is the amazing data science team that I have the privilege of working with every day. And so we do lots of fun things, one of which I will talk about in this talk. All right, so Duo Security, some of you may know this, but if you don't, one of the main things that we do is provide two-factor authentication services. So a company might protect some of their applications behind Duo, and then when a user goes to log into that application, they'll type in their password and then receive some sort of opportunity for a second factor of authentication. So we might send a push to their cell phone, or they might have a hardware key or something like that. So in this case, the user receives a push to her cell phone and is able to approve or deny that authentication request and gain access to the application that they're looking to gain access to. And so you might imagine that this process results in a bunch of data, namely authentication logs, where we or the company who has these users can look at that set of authentications and try to understand something about what is normal behavior for users and what might be anomalous or indicative of fraud. So in a broader sense, this is part of the idea of user and entity behavioral analytics, or UEBA, and this is something that is not specific to the authentication context, but seen across the industry. And the basic gist here is that we hypothesize that users behave according to some patterns, and then if we can model those patterns of user activity that are expected, we can then find deviations from those expectations, and that might indicate fraud or attacks or intrusions into the network. So in the case of this authentication data that I'll be talking about, the behavior that we're talking about includes a lot of different properties of the authentication record. So this could be things like the application that they're logging into, the IP address that they're coming from, all sorts of things like that, as well as the timing and ordering of these authentication attempts or authentication records. And that's actually going to be the primary focus of this talk, is that part that's about the timing and the ordering. So our specific instantiation of this UEBA idea is, here's a screenshot from a blog post about it. It's a product that's currently in beta. We're testing it with a core group of customers to try to understand which features are most useful and what things we can improve and how our models might iterate. But the basic gist is that we provide to an analyst or an IT administrator at a company some information about the authentication record for their users. So we are able to highlight authentications that are particularly unexpected given the history of their users, and then that helps them prioritize their investigative efforts. All right, so this is fundamentally an anomaly detection problem. To a first approximation, all of this data is unlabeled. We don't have very good indicators or labels that indicate that this was actually fraud, or at least not enough to do anything with from a machine learning perspective. So we're dealing with an unlabeled, unsupervised learning situation, and we're doing anomaly detection. And as with any sort of anomaly detection problem, this kind of has two steps. One is you have to model the expected behavior, and then you have to identify deviations from it. And so obviously the challenge is in the details here, because what exactly is the appropriate model of expected user authentication behavior? What should we use for that? So when people hear anomaly detection, often this is what pops into your mind. So we have some idea of independent draws from distributions, and we want to do some sort of density-based estimator that tells us something about the expected distribution of events, and then we find ones that are in low density regions, and we identify those as anomalies. why might this not be exactly the right approach in this case? So the first thing that is most important for this talk is that this is assuming independence between authentications in a way that really is not accurate to the actual data. So if I'm trying to log into an application and my cell phone is in the other room and I miss the push authentication, I'm more likely to go get my cell phone and then log in again immediately afterwards. Or I might have a sequence of authentications that represent some larger activity that I'm trying to accomplish, and so you see those sequences repeated. There's also temporal patterns that are very, very strong in this data. You authenticate in the workday, you have patterns when you get in, you don't authenticate at 3 in the morning very often, and that's a little bit harder to get into these kinds of models, although not impossible. Like I said, this is an unsupervised problem, and anybody who's done anomaly detection with unsupervised data, it's really hard to know, like, where exactly do you draw the lines around that distribution, what's actually weird, what's normal, and sort of related to that, it's hard to evaluate the quality of models or the model fit, or if you have 2 different models, which one do you want to use for your application? All right, so one of the things I've emphasized is that this has this temporal component, so what if we just model this as a time series? So what you're seeing here is data from one company where I've binned the authentications to the hour, and so the y-axis there is the number of authentications for a particular hour at this company. And you start to see these really strong temporal patterns that I was talking about. You have a daily cycle. This is a little over a week, so those 5 peaks there are the working days. And so this looks like, you know, a time series. There's a huge literature in time series analysis, so maybe we can do that. And we can, and this makes sense for aggregated counts, but that's missing a piece of the puzzle here, because one of the things we really care about is sort of the unaggregated sequence of authentications from a single user. And so that's a much sparser sort of discrete sequence that is a lot harder to represent with a lot of this type of model. And we're interested in some of those patterns for sort of the anecdotes I gave a few slides ago. So if we're interested in the sequence of authentications from users, maybe we can use sequence models. So things like Markov models or hidden Markov models, where we're saying, oh, let's model the probability that you do action 1, followed by action 2, followed by action 3, or let's model something about the state that you as the user are in, and that might reflect something about your authentication activity. And this is potentially interesting as well, but in capturing the probability of those sequences, we have now lost all that information about time. All right, so all of this was building up to point processes, which was in the name of this talk. And so the idea of point process models is that we want to represent the data, or we do represent the data, as a sequence of events that are situated in time. So think about our authentication record as just a set of event times, where each event time represents an authentication. And we can think about that, you know, I've represented it here where each vertical bar there is an authentication happening across time. And the idea of point process modeling is that we try to model the probability of an event occurring in a small time window as that time window goes to 0 around a particular point in time that we're interested in. And so I have an equation here that I'm going to zoom in on just a second and try to sort of give you the intuition of what that means. So the idea of a point process is that the thing that we actually model is something called the intensity function, which, as I just mentioned, is the probability of an event in a small window of time. So the intensity function, typically represented as lambda on the left-hand side of the equation here, is the probability of the count of events in a window being greater than 1, or greater than 0, sorry, as the size of that window goes to 0, given the history of the process and any covariates that you want to include in your model. And so here's an example of what one of these intensity functions ends up looking like. So this is just an intensity function fitted to data representing the probability of authentications over the course of a day. So here you see, I think that 0 approximately is midnight here. And you see that people are not authenticating at 3 in the morning, and people are authenticating, you know, when they get to work, which is totally reasonable and matches our expectations. This kind of modeling is not new in any sense. This has been around for ages. In many domains, there are very specific mechanistic models of these intensity functions, where, for instance, in seismology, they talk about earthquake modeling and aftershock modeling, and there's a lot of physics that gets kind of pulled in and understanding of the dynamics of that. Similarly, neural spiking models use these a lot, so the idea of when is a neuron in your brain going to spike. Again, there's a lot of understanding of the physics behind that. That's actually where I first encountered this kind of modeling, was back in grad school doing neuroscience stuff. Also astronomy, ecology, that kind of thing. These appear all over the place. So these models are often fit using just sort of maximum likelihood, clever optimization, take your intensity function and fit it to data. But that means that you have to sort of engineer this model fitting solution for your particular intensity function, and that can be kind of annoying. And so I'm going to show you a trick in just a second for how we can make these a lot more accessible to our problems. So there's a lot of different ways of representing these processes. So I talked about thinking about them as just a set of event times. Equivalently, you could model the waiting times between events, or you could model the cumulative count of events over time. All of these representations are staying in this continuous space where we're saying, okay, there's points and they fall in some space in time. But we can also play this trick and discretize the process. So we can say, okay, let's take little tiny time windows such that the windows are small enough that at most one event occurs in that time window. There's math that I'm not going to show you here that shows that if you do that, you can show that the likelihood of that binary process converges to the likelihood for the continuous process as those time windows get smaller. But what this means is that we've suddenly converted this continuous time modeling problem into a binary regression problem, more or less. And so we can take all of these standard toolkits for GLM or your Poisson or logistic regression that we are very familiar with from a lot of our work, and suddenly we can apply them to these problems. And so we've taken a continuous problem into the discrete space, and we've also taken an unsupervised sort of density estimation problem that I started out with and made it into a supervised modeling technique. All of a sudden we have zeros and ones, those are our labels, we can fit them to data. And so that's pretty cool. And like I said, it allows us to use tools that we're used to, and it makes this really fast to try whether these models are actually going to be useful to us in practice. So you discretize your data into that binary representation, create whatever feature space you think is important, and I'll talk about that a little bit in a minute, fit the model using your favorite tool for GLMs, and then evaluate it, and that's actually a really cool point I'll get back to at the end of this talk. All right, so just to sort of hammer this home, this is that same example of the intensity function that I showed earlier, and this is where it came from. So I fit a binary model to data where the only features I had in this model were the hour of the day. That's it. That's all I included. I projected it using a regression spline basis to get the smoothness there. But this is a really, really simple model, and it sort of intuitively matches what we expect to happen. So the vertical lines on that plot are disappearing a little bit, but you can at least see that the places where the intensity function is high is where we're seeing the most authentications, and where it's low is where there's fewer. And you can do this for time of day, time of week. You can start to capture all of these periodicities that you expect to see in this data. But one of the things I sort of motivated this approach with was this idea that there's dependence between the authentications. It's not just that there's temporal periodicities, it's that when I see an authentication from a user, that actually changes my expectations of whether I'll see another authentication immediately thereafter. And this is often referred to as the idea of sessions. So authentications occur in groups. Those groups are often referred to as a session. It's an activity that the user is doing. And we can include that kind of dependence in these models relatively easily by just including history features into our feature space that previously just included the time of day and time of week. And so when I say history features, what I mean is you have a feature that says, how many authentications did you see in the last 3 seconds? How many authentications from this user did you see in the last 5 minutes? Last week, this month, whatever it is that you want, you can make those more specific. But even with just very, very simple binned counts of authentications, you can start to see some really interesting patterns. So here is a fitted intensity function to about 3 and a bit weeks of data. And you can see those daily and weekly cycles that you expect. But you can also note that the second week there looks a little different than the others, right? So what's going on there? Turns out that's the week between Christmas and New Year's. So there's a lot fewer authentications happening in that week. And what this model is able to do is say at the beginning of the week, I'm seeing fewer authentications than I expected. And so the model's predictions of the probability of seeing other authentications are sort of damped down for that week appropriately. So this is capturing periodicity as well as sort of eccentric patterns in the data. And you could think of a lot of uses for this. It's a pretty neat result. But we can also zoom in. I talked about wanting to look at user-level behavior. And so if you take one of these models and train it on just one person's data, and then look at what the predicted probability was for each of their authentications, you get something that looks like this. And what you see is, I have a bunch of colored points here that you can mostly see. So the color comes from an independent sessionization algorithm that we had where we tried to sort of identify which groups of authentications represented a particular session from the user, whereas the Y position of those dots just is the prediction from this point process model. And what you're seeing is that as a session progresses, the model is saying that it has a higher expectation of seeing additional authentications from that user, which is exactly the sort of pattern that we wanted to model here. So now, as a session progresses, it's less surprising to be seeing these authentications. All right, so I mentioned that evaluation was one of the really cool things here. So we are using this discretization of this process, but a lot of the theory is coming from this continuous world. And in the continuous point process literature, there's this idea called the time rescaling theorem. And there's math there, but I'm going to explain what that math is in just a second, so you don't actually have to read it if you don't want to. So the idea is that we can evaluate the goodness of fit of one of these models to our data by rescaling the events in a particular way I'll describe in a minute. And then if that intensity function describes the generative process of the data, then we have an expectation that the waiting times in the rescaled data will have a particular distribution, and we can compare empirically against that theoretical distribution to get a measure of fit. And so the way that that rescaling works is that we are moving events sort of closer and farther apart from each other based on the integral of the intensity function between them. So in these first two events, they're far apart in time, but between them, the intensity function is very low. We don't actually expect to be seeing frequent events in this region. And so they kind of get pulled together. Whereas between the second two events, the intensity function is pretty high, even though the events are close together, and so that integral is higher, and we kind of pull them apart. And so then we look at this process down at the bottom, which is the rescaled version, and we look at those waiting times, which are like those orange and blue bars, and compare them to an exponential 1 distribution. And this is the sort of thing you can do using PP plots or QQ plots and KS tests and things like that. It's sort of statsy things, and if you aren't familiar with them, you can find a lot of tutorials and things about how to do this. But the basic idea is that if the model fits the data well, we would expect these lines to fall on the diagonal of this plot. The empirical CDF would match the theoretical one. And so these plots are showing the models that I've been talking about in this talk with one extra one. So the bottom line in the middle there, the blue line, is actually the constant model. So we don't model anything. We just say what's the overall rate of authentications, and we'll use that. And then as we add in the daily and weekly temporal features, we get closer and closer to a good fit of this model. And then as we add those very simplistic history features, it's actually pulling it in on the right to something that, at least at this scale, is very hard to differentiate from the diagonal. So what have I talked about here? I've motivated this problem as we want to model the expected user authentication behavior in order to support anomaly detection. This behavior is very dependent on time as well as previous authentication activity from that user. Point process models are just sort of one reasonably accessible way of trying to capture these patterns for this kind of data that it can be represented as these discrete points in time. And by doing some little tricks with discretization and things, we gain access to model fitting libraries and quantitative model fit techniques that let us have like a lot of really easily prototyped approaches to these problems. So I've, in 20 minutes cut a lot of corners and left out a lot of the details. So I started at the very beginning by saying, hey, authentication behavior is this highly multidimensional thing where we have the application that they're logging into and the IP address and the kind of second factor they used and their username and like all sorts of stuff. And then all of a sudden I just forgot about most of that and said, hey, we can represent authentications as points in time. And that's a simplification that makes this kind of modeling a lot easier, but leaves out a lot of the details. So in our work, we're working on methods to incorporate sort of this kind of point process modeling with ways of also modeling some of those other dimensions of the authentications. If you only have a couple of dimensions, there's something called a marked point process where you can sort of use a multinomial instead of a binary regression and sort of model several categories, but we have hundreds of categories and that sort of degrades very quickly. So that's one thing that we're working on now. The other is that we really care about these user-level models, but often users have very, very little data. So a user might authenticate once a week or a few times a year even. And what do you do with those people? This kind of thing is going to fall apart because you just don't have enough data. But maybe now that we're using these sort of well-understood modeling techniques, we can start to do some sort of hierarchical or multi-level model where we're sharing information between users or between users and a company level model to try to be able to do something with those sparse data users. And finally, one of my goals of this talk here, none of this is new modeling, this is all stuff we pulled out of the literature, but I haven't seen it applied to things in the security domain. And so I'm hoping that something in this talk has triggered something in the back of somebody's mind here to think about whether there are problems that you're working on that could be represented in this way and maybe use these approaches fruitfully. If you do care to look in more detail, this is a very, very abbreviated list of references that I found useful when learning about this stuff. It's a little biased towards neuroscience because that's where I come from. But it's pretty generic, the description of this modeling approach. So that's all I have. Thank you very much.
Okay, thank you so much, Bronwyn. That was very interesting. I'd like to start the discussion off. Let's see, I jotted down several questions, but one gets at something you talked about a little bit towards the end. My question is about all of the point process modeling you talked about. The goal is primarily to detect these anomalies over time for a given specific user. There's a separate question, of course, you could ask, which is cross-sectionally, what users are unusual relative to other ones. So one question I have is, are companies generally more only interested in the first question rather than the latter? And secondly, would the point process modeling be an appropriate way to address the second question, where you're basically not looking for anomalies outside of the typical, what you would expect given the intensity function, but using a metric of how different intensity functions are and looking for basically weird intensity functions that you predict?
There's a lot of pieces to that question. All right, so one of them was about, okay, so let me see if I can remember this. We're looking at weird authentications for a user, but what about looking at unusual users? So a lot of the use case for this assumes that you have particular users who, if you have really strongly authenticated to be trusted on your system, if you set up all of these second factors and things like that. So you often don't have sort of extra users just popping up. And so a lot of the sort of particular problems we're trying to solve with the UEBA product assume that you have, all of your users are benign, but sometimes somebody might be being a victim of some sort of account takeover. On the other hand, this idea of clustering users and understanding different patterns of behavior is actually something that's also interesting for a lot of different applications. And so it's sort of a side effect of a lot of this modeling that, hey, maybe we can start to think about do people in different departments have different patterns, or maybe they're riskier than others and we want to have different amounts of friction for the authentications for those users, or maybe we want to use that clustering to support that sharing of data that we were talking about earlier. So there's a lot of interesting directions to go there, and I think it's worth noting that some of these models are interesting even outside of the anomaly detection context, where we're just saying, hey, we want to be able to predict the load on our service for a particular point in time, and this is not something that we're working on now, but it's a place where these models could get extended, I think, in the future.
Hey, awesome talk. I think my question is related to something you had on your last slide there. So point process models are very useful for these series like neural spike trains and the authentication data you mentioned, where we have only a single kind of event that we care about, and we want to know when it's going to happen, right? An action potential happens or it doesn't. Is there an extension of this kind of model where I want to know not only when is something going to happen, but when it happens, I can have one of a set of possible things that occur? So the thing that's in my mind is, if you have a series of financial transactions, I want to know, someone's going to have a transaction and they have that interaction with another entity. Or maybe if it's web data, it's like this IP sends a packet to this other IP at a certain moment in time. Have you heard of any version of that kind of?
Yeah, there's a lot of different ways to try to approach that problem. So one is to do the thing I alluded to briefly, which is to put marks on your point process, which essentially is just modeling multiple categories of events, and so you can do that independently or as a multinomial, but that doesn't scale very well to more than a couple of categories. You can put anything you want into the feature space, so you can do things like, I'm going to predict the probability of some authentication occurring based on the number of failures and the number of things from all these different applications, and you can get as complex as you want there. And then one thing that we're exploring for doing that second piece that you described is to say, okay, well, we want to predict the probability or the expectation of some authentication occurring, but then on top of that, we want to model something about our expectation over the type of authentication. So this is coming from the wrong country. So even though we expected an authentication at this time, we didn't expect it to be from Russia, so this looks weird. And so, one approach to that we've just started looking into is essentially a hierarchical model where we say, it's not quite right, but we're going to assume that the probability of some authentication is sort of independent of what the properties of that authentication are. And so first we model the probability of the authentication, and then we say, okay, now let's model something about the expected distribution of those categoricals. It's not the most satisfying answer in the world, but it gives us something to sort of combine existing models that we have of independent anomaly detection on the properties with these models that can capture something about the temporal patterns. It's a really interesting question. If you have a solution to it, I'd love to hear it.
Cool. So next question. Awesome talk, by the way. So one of the things you're kind of alluding also onto this last slide is sort of maybe there's some sort of grouping that's between user level or company level, so like some sort of cohort-based analysis. If you were to choose between like geospatial grouping or like role-based grouping for sort of grouping where like, do you have any ideas on like which might be better to start off with or anything like that?
I mean, I think for this problem, we've definitely gone towards the role-based grouping because it makes, I think, more sense for the application where you're talking about a company and their users. There are companies where obviously there's going to be geographic issues, the larger ones, but for smaller companies, maybe everybody's in the same place, and so that role-based grouping is much more important. So like anyone hitting the production system who otherwise looks like a marketing person, maybe that's a weird thing because they're accessing systems we wouldn't expect them to access. One of my coworkers did a fun thing where he clustered users together and then asked us to predict which other user in our company we were most similar to. That was a fun exercise. But you can look at patterns of behavior and try to understand functional groupings of people, and we're hoping to do some evaluation of how accurate those are relative to org charts and things at some point in the future.
Yeah, good talk, thank you. Have you done any operational validation of your model to say, for instance, with our traditional detection techniques, with our regular SOC, how many of those would have actually been detected as anomalies with your system?
Not quite that particular situation, but we, as I mentioned way at the beginning, one of the things that we're doing is we have this UEBA product in beta, and we've been doing this active developer, I think that's the active development program, something like that. Anyway, we're working with particular customers, and as we've been developing these algorithms, have been showing them lists of the authentications that our system was flagging for their company and asking them, hey, does this make sense? Is it something that you would have flagged? And that's not at the scale where we can use it for training, but it is at the scale where we can start to understand patterns of behavior in our models that maybe do or don't match their expectations. I think it's actually, side point, a really interesting and important step of model development for these kinds of applications. One of the obvious flaws there is that we're typically working with smaller businesses that don't have a SOC, really. And so they're giving us feedback on the things that we flag to them, but we're not getting feedback on the things we're missing. And so it's a very asymmetric feedback system, which is not ideal, but we're hoping to have more of a sort of real-time feedback loop eventually in the product.
You started to hint at it at an earlier answer, but I'm curious if you've done any kind of like insider threat modeling, like our web dev all of a sudden hit back-end source control and then an FTP server, something like that? Yeah,
it's not something that we've worked on explicitly. Our threat model at this point is pretty much like account takeover and push phishing and things like that. But it is definitely something that is an obvious extension to this work where, okay, it's not just people in other countries, or like the differences might not be that big. It might just be these small differences in activity patterns within the company. But it's not something we've explored in depth yet.
All right, I had a quick question. So so this inspired by the hurricane. Like my family's in a panhandle, and so I was thinking about in terms of like a disruptive event that can change behavior. So I wanted to get your thoughts on like modeling something where there's some disruption that changes your behavior for a long period of time, and like how do you think you would kind of address that, because that becomes the baseline for a period of time until it doesn't again.
Yeah, so there's a lot of different directions to go with that. One, I mean, the less dramatic version of that is that we'll often flag authentications, and the person will say, well, actually, that person was on a business trip, that's why it looks weird. And so there are these benign explanations for anomalous behavior. So there's a couple of points there. One is that anomalous doesn't mean malicious, and that's something you always have to keep in mind when doing this. Another is questions about model retraining, and when do you try to update your models and using what data. Some of the strength of things like point processes is that if those business trips are things that you see in users generally, in theory, you could probably get a model that would sort of recognize that pattern as a particular pattern that represented weird behavior for that user that was expected at the company. And so that's something that we can't, we're not doing currently, but is an interesting extension of this kind of work. But at a higher level, it's also one of the reasons why, the output of this model is sort of a ranked list of things with some explanation of why we think it's anomalous. And the goal currently is for the IT administrator, the security professional at the company to look at those and interpret them in context. And so we're trying to provide useful context to help them do their job faster. But for reasons like that, this is not something that currently can sort of operate independently.
Cool. Thank you so much.